So today we are going to whatever we finish today, that's the end. Okay. So I will see if I can finish this topic, which we already started. So we have gone through the theory, which is about signal design. Okay. And on Wednesday you will have what? What time? Sure?
Yes.
Okay. And that will be online, okay? Although we are on campus, but that seminar will be online. So speak as somewhere else. Anyways, what we looked at last time was this equation, which gives you, they call it desirable cycle length, but you can call it design cycle length. For some reason, they keep on playing with these words. They mean the same thing, but they just want to show that we know more English. Okay, so design cycle length or desirable cycle, whatever it is. Number of phases. Last time in each phase, saturation headway. What is this? Peak hour. V by C ratio, volume upon capacity ratio. We select the ratio. Okay, we select the whole ratio to put into this equation. Okay, and this is the demand volume. Okay, so let us look at an example where we can use this equation. We have 3 phases. Let me write it down. We have 3 phases. Each phase has a loss time of 4 seconds. Saturation headway 2.2 seconds. Peak hour factor 0.9. VC 1200. VC, yes. Any problem? There, right? V by C ratio changes from 0.8 to 1. So it's not one value, we have to try the range. Okay, rest of things are constant. Anything missing? No, right? Okay. The only thing is this ratio can change. Okay, you can go from 0.8 to 1. And you can try different values to see what happens. Okay. So for example, if I try the value of V by C ratio 0.8, how much cycle length will I get if I try 0.8? How much? Last time I was done. Negative? It turned out to be negative, right? Okay, what about 0.9? If I put 0.9. What I used to do in my exams. face for it with 0.8. Okay, anybody else? Same? Same? They bring their friends together so they can have seen that. Okay? But anyways, it's negative, right? Six, 4, 8. Okay, what about 0.9? How much do I get with 0.9? 1, 2, 6. 1, 2, 6. Okay, and with 1? 0.8, 0.9, and this one is 60 point? 64.8. Okay, there is one negative value. Okay, but it's time, right? It's time. Time can be negative? No? No? You will never invent time machine, right? Time is negative, you can go back in time. When I was young, we were kids. Right? Nobody is saying they are still kids. You are old enough. Okay. So, cannot be negative. So, this solution gone. Cannot use it. Okay. We have two other solutions. They can be others as well if you try more values 0.8, 1.8. Okay. But we have two other solutions 126 and 64.8. Okay. Which one do you think is better in terms of time? If I just look at the time, which one is better? If you are the driver, which one is better for you? Cycle length of 64 or 126? 64? 64, right? It's less time. You have to wait less. Okay. But what's the problem here? This is at V by C ratio 1. So what's the problem? If I take 64.8, the drivers have to wait less, but if V by C ratio is 1, that means what? This say again? Flow equals capacity. There is no margin now. Okay? There is no extra space left. So this is a very risky situation. Okay? You have to go with slightly higher value. Maybe not with 0.9. Maybe you can try 0.95. It will give you a better value than 126. Okay? But to take a value at 1 will be very risky. Get it? There? Okay? Okay. Then we have this question. We have two one-way streets. This is one way, this is one way. Okay? So whatever right turn happens, it will happen, permitted. Okay? If I open this signal, okay, so this guy can go in this direction as well because this guy will be closed. Okay, and same thing here. If I go open this signal, this guy will be closed. Okay, so he can go straight and take the right turn as well. Okay, so how many phases I need? I need only 2 phases. Okay, so it's a very simplistic design. You have two one-way streets crossing each other. So two phases can work here. And I told you how. I'm just giving one phase to each road. That's it. Because nobody is coming from the other side. Okay, but if I had this and this both, it will not work. Two phases will not work. Somebody is coming from here, I need a phase for him, and somebody is coming from the other side as well, right? He may also want to take a left turn, so he may need a separate phase. Got it? He or she. She, huh? I should change my whatever you call it, pronouns in this class. You guys made some pact or something, no boys will register in this class, something like this. Huh? What happened? Okay. You can see the rest of the parameters? Okay. Now the problem is we have to find out the number of lanes. Okay, we have to find out the number of lanes. And then after you find out the number of lanes, you find out the desirable cycle length, the one which we were doing here. Okay. Now there is a cycle length given here. Okay. Is this my desirable cycle length? Maybe. I don't know. This is just an initial assumption. So we can start the problem and find out number of lanes. Until you find out number of lanes, okay, you will not know VC for sure. Okay. So this is why this assumption is given. So using this assumption, I can find out my VC. Okay. Okay. So this is just because you cannot see it here, but you will see when we finish this problem that VC depends upon number of lanes. Okay. And without VC, I cannot have the desirable cycle length. Okay. So there are two unknowns, and both of them are in the same equation. VC and desirable cycle length. They are in the same equation. So until I fix one, I cannot solve the other. Clear? Okay. I believe they make you do this in numerical methods where you can find out like more unknowns from less equations, right? They do that, right? Nobody? Right? Okay. So if you have to do something like this in the exam, she is responsible. Yes. She said you have to do it. Okay. Anyways. This is the equation. We are trying to find out what first? VC. Okay. So I will use the initial assumption. I have two phases. Sorry, and two phases. Okay. How much is the lost time? Where is it? 4 seconds per phase. Okay. So TL is 4. So two phases. This is 4. This is 2.3. Peak hour factor is how much? 0.95. Okay, VC we don't know yet. Okay, and what is V by C ratio? What is my V by C? 0.9. Okay, so using this equation, give me the value of VC. You can use the other equation as well. Why? There is another equation for VC value. One, 135. C is given. Initial value is given. Okay. Any questions? Any problem? All clear? Okay. Now this value tells me if you are having a cycle length of 60 seconds, then the demand volume should be below this way. Clear now? The demand volume which the signal can handle with a cycle length of 60 and these parameters is 1357 demand volume. Okay. Now if I look at my problem, now when we say the cycle can handle this much volume, this is total. Total. Okay. If you look here, how much total I have? 1200 here, 1800. Total is 3000, right? Okay, which is more than this. Okay, now here you will see the impact of number of lanes on the total volume. Okay, right now we are saying one lane here. So if there are 1800 vehicles, all of them will pass from one lane. Okay, so they will pass one by one. So all 1800 of them need some signal time, right? Clear? Okay. But if I make two lanes here, then I can pass two vehicles at a time. Okay. So I don't need the full signal time, I need just the half. Clear or not? Okay. So I will not have 1800 passing one by one. I will have 900 passing one by one, right? 900 from one side, 900 from the other side. Clear? Okay. So if I take 900 here, so 900 here, and this one, let's say I don't do anything with it. I keep it one lane. So 900 plus 1200. Okay, I'm checking one lane volume. Okay, so here I divided that 1800 into two lanes. So per lane became 900. And 900 from here, 900 from here, but together, right? So total 1800. And here 1200. So total is how much now? 2100. Did I satisfy this? Not. Okay. So that means I should increase more lanes, right? Where should I increase? Down? For this direction. Why? Why not just keep on increasing here? Symmetry? Very good. Good architecture. We don't want symmetry. Yes. The reason is what? The reason is you have per lane how much here? And per lane how much here? 1. So logic says try to reduce the higher one, right? Okay. So that's why. Okay. So we'll go with this one. So now this 1200 is divided to 600 each. Okay. 600 plus 600. Oh, sorry, 600 plus 900. 1500. Did we reach this? Not yet. Now we have to increase this one, right? This one is higher. So I increase this one. Total was 1800. Divided by 3. How much? How much? 600. What did you say? 300. 300. 1800. Okay, you always go back to the initial one. 600 each. 1800 will divide by 3. Okay, so 600 here per lane, 600 here per lane. How much total? 1200. Okay, so this can work. With the initially assumed cycle length, these number of lanes will work. If I have to move forward, I have to move forward with this assumption now. Okay. So I first fix the cycle length so I can find out DC, and then DC led me to find out the number of lanes. Now I can go back to the cycle length again because that was just an assumption. Okay. So I'll go back to the equation where I find out the desirable cycle length. Okay. So everything is known here. How much is VC now? 1001. Clear? Okay. Any questions? No? Any answers? No. Fine. Number of I? What? N value is 2. 2 phases. 2 phases. Much faster online. Much faster. So my desirable cycle length is 77.4 seconds. Okay, and not too much. In the end, you will round it off, right? In the end, we will round it off. Okay, so we can round it off to 80. Normally, we round it off to the nearest 5 or 10 second multiple. Okay, so even you will see it in the books, even 78 or 79 is not taken. We just round it off to the nearest what do you call it? Full number, whatever. Okay, so not the full number, nearest 5 or 10 seconds multiple. Clear? Clear? Okay. Now let's say we came up with this design, and people in the ministry said that the road space is limited. Okay, the road space is limited. So you are asking for 3 lanes here, but we can only give you 2 lanes. We can only give you 2 lanes. Okay, so if I make 2 lanes here, okay, in the 1800 direction, so 1800 divided by 2, right? Which becomes what? 900. Okay, so my VC will be how much? Clear? Okay, no problem. We can still calculate the cycle length for this VC as well, because we are just using it using our first assumed cycle length. Okay, but the first value was assumed. Okay, so I wanted to assume it so I can fix this. Okay, so I will just discard my assumption. I will go with the number of lanes given by the government. The maximum lanes they can give is 2 and 2. So my VC is fixed from the government now. Got it? Okay, so if I fix VC as 1500, how much you get here? Negative, right? Okay. So that means what? You are 5. You are 5. Okay. But anyway, you have to come up with some other solution. Okay. What other solution we have? What did we do the last example? Yes. What do you say? Error. What did we do in the last example? We can. Okay. Clear now? Okay. So we didn't cover the signal design, full signal design, but we can just have a idea about it, that we can change these things within the desirable cycle length equation. Okay, and you can see what happens. Some of the things you cannot change. For example, H, saturation headway. It depends upon driver behavior. Okay, minimum headway. Peak hour factor depends upon traffic trend, how they are going up and down, 15 minutes and whole hour and so on. You cannot change. We can change this. We can do something to change this. Okay. We can do something to change. We can play around with the number of phases as well. Okay. This one again, driver behavior, lost time. Clear? Okay. So the other parameters which we can work around with, we can see what happens. Okay. Once you have found out what you are doing here, if I have 2 lanes, total was 1800. I made it into 2 lanes. And what did I do with the volume in these 2 lanes? I divided it what? Equally, right? 50% here, 50% here. Is this what happens? No. Okay. So this equal division is not the real way. Okay. Another thing, there is no turning, right? If you are providing turning, there can be a lane which will have turning movement as well. If I am making multiple lanes and there is a turning movement. Okay. So most probably you will see that some of those lanes will have turning, some of them will not have turning. Yeah? So do you think, again, the volume cannot divide equally then. The people who are taking the turning will eventually go to that way. Clear? So this brings us to the concept of critical lane. Critical lane is which one? So you have, I am designing for this phase. Okay, and I have 3 lanes here. One of them can be critical lane. Why? I told you the reason. Because volume does not divide equally. And can be for different movements as well. Okay? So which one should be a critical one out of these 3? What is the criteria? The one which has what? Higher volume, right? Most probably yes. The one which has higher volume, most probably yes. In most of the cases, it is true. Okay? But for example, if I have 2 lanes, by chance, both of them have same number of vehicles. Just by chance. I have one lane for straight, one for left turning, and both volumes in the peak hours are equal. Then what? Which one? Critical lane. Volumes are equal. Then what to do? You said higher volume. Volumes are equal. Then that has a turning wire. The answer is correct. Yeah. Take more time, right? Okay. So this is how we generally define the critical lane. Okay. Not on the basis of higher volume, on the basis of higher time. Because what are you designing? 20-story villa. What? What are we designing? Nobody knows, right? What are you talking about? What did we design? Intersection. Demand, capacity, yes. What other words are used in the class today? Yes. Cycle length. Okay. One of my daughters, when she is in a bad mood, she will not give me answers. I tell them what were you saying? I will not tell you. She is very good. Okay, but she is always like this. She doesn't wait for the bad mood. Cycle length, right? Cycle length is what? Time. Okay, so critical length should also be the one which needs more time. And now you know that more time does not always mean more volume. Yes. Okay, so turning can slow you down. What else can slow you down? If you are taking a turn, you are going straight. Turning will take more time, it will be slower, and it has more radius, right? Straight is less distance, turning is more distance, right? What else? If I have 2 lanes, both going straight. Both will have signal, right? But what may slow down one of them more than the other? If there is a shared movement, yes. So there is a lane which is for straight, but it has the right turning from the same lane as well. Yes. What else? Anything else? If both of them are exactly for straight. Driver behavior, okay. That's why we have the lost time and the saturation benefit. But this is already taken into account. What else? Heavy vehicles. Okay. The lane which has higher percentage of heavy vehicles will eventually slow down more, right? Okay. So when you do the signal design process, when you are dealing with the phases, you found the cycle length. Now you are looking to divide the cycle length into different phases, different directions. Okay, so in each direction, for each phase, there should be one critical lane. You cannot design for multiple lanes at the same time. Okay, so there is one critical lane, and that critical lane is the one which needs more time. And we are using parameters here which may change according to lanes. For example, lost time. For example, headway. The headway is the distance between, or the time interval between 2 vehicles. It can be different for turning. It can be different for heavy vehicles, right? It is different. Okay, heavy vehicles do not keep maintaining the same headway. They do not have the same lost time. Okay, so when you fix your critical lanes, when you know the critical lanes, okay, you may go to the highway and you find out these parameters for that lane. Okay, so the rest of the design, the main point is, the rest of the design is for that lane only. Once you have finalized the critical lane, the rest of the parameters are for that lane only. Okay? Okay, anything else? Yeah. So every phase should have one critical lane and there should be no phase without a critical lane. Okay, every phase should have one critical lane and there should be no phase without a critical lane. Okay, and then that means what? Whenever a phase opens, whenever a green happens, at least one critical lane will move. Okay, because that phase is designed for at least one critical lane. Okay, then there can be phases where you have multiple critical lanes opening. Okay, these phases are called as overlapping phases. Okay, so the possible combinations of overlapping phases can be two straight movements. They can be overlapped. These can be overlapped, right? Okay. This can be overlapped. Okay, straight and left. Okay. So you may have different possibilities of overlapping the phases. Okay. Overlapping, when you do overlapping, it saves time. Because you are allowing more movements simultaneously. The same thing which we are doing with number of lanes, right? Open different lanes simultaneously, and the cars will go side by side. Okay. So same time, but more cars served. Same thing happens when you have overlapping phases. Okay. It saves time. But now I have different options. Okay. So how do I select the option? Again, I'll go back to the critical lane of each phase I'm overlapping. And I will sum those volumes for the critical lane only. Okay. So for example, in the first combination, two straight, this one has a critical lane volume of 150. This one has 300. This one is 150 again. This one is 250. This one is 300 again, and this one is 350. Okay. So if I allow these two together, I will have how many vehicles going together? 150 plus 300, 450, right? If I allow these two together, 150 plus 250, how much? 500. Okay, better or worse? Is this one better than this one or worse? Huh? Worse? 450, 500. 400? Yeah, 400. Okay. So worse, right? Why were you saying 500? Okay. So 400, worse, right? So this overlapping is better. It will serve 450 vehicles at the same time, and this will serve only 400 at the same time. Okay, and if I go here, 650. Okay, so this one is the best one. This will serve more vehicles at the same time. Clear? So in overlapping phases, we look at the combination of critical lanes. So this is the only time where we are looking at the combination of lanes, when we are overlapping phases. Okay, but keep in mind, these are overlapping phases, not the same phase. We are still considering them as two separate ones. Okay, but some part of their time is together. Clear? So they are designed as separate phases. Okay, but in the end we are trying to merge them together. Clear? Okay. Okay. We have talked about delay studies earlier as well with travel time, and we have calculated delay for which type of intersections. We calculate delay for two types of intersections. Which ones? Nobody knows. Multi-lane highway and freeways. Very good. Both of you are wrong. You are asking what was the third one, right? Yes. These are highways, but not intersections. Yes. Signals and outputs. You still check. I don't trust people. My notes are better because they are given by Dr. Lee himself. Roundabouts and signals. Okay, roundabouts and signals. Okay, and at that time we called it what? What are we calling it here? Yeah. Anyways, at intersections there are measures of effectiveness. Okay, measures or values by which we measure the performance of the facility, performance of that spot. For multi-lane highways and freeways, it was density. Okay, so if you want to measure the performance of traffic flow on these highways, you will use density. For intersections, we use these three. Sometimes you use all three of them. If you use any software for traffic flow analysis of intersections, you will find all three of them being used. All three of them are calculated. Okay, but if you are talking about level of service, then delay is used. Okay, so we will talk about delay in detail, but delay basically means the difference between the actual time and the ideal time. Ideal, right? The difference between the actual time and the ideal time. Okay. If we are talking about the intersection, ideally, when you reach the intersection, you should pass without stopping, without slowing down. This is the ideal, right? Okay. So delay is considered when there is a difference between your arrival and your departure. Any difference between your arrival and departure is considered as delay. Okay? For an intersection. Then we have queue length. The queue length is measured in number of vehicles. Queue length is longer, that means performance is low. Okay, and then we have stops. We have used fraction of vehicles stopped. If you have 100 vehicles, out of those 100 vehicles, how many have to stop at the intersection? Okay, so we have used here. If this fraction is higher, that means performance is low. Okay, okay. It can be taken as proportion, or it can be taken as a number as well. When we consider delay at the intersection, we can have three types of delay. We can have stop delay, approach delay, timing queue delay, and travel time delay. Okay, stop delay we know it's very simple. Right? The name says what? It's delay man car. Okay. We have approach delay. Approach delay is the one which we call as control delay early. This is the one which we calculated for signals and on-roads. Okay, it has three parts. What? What does it mean? How is it different from stop delay? What is the difference between stop delay and approach delay?
Stop equals 0. Approach the speed limit slowly until we reach the roundabout entrance or.
Okay, and that's it? Yes. No. The deceleration and acceleration. Okay, so all this is included in the approach delay. We call it earlier control delay. Means the same. Approach delay or control delay means the same. So it has more than just a stopping. Okay, and stopping may happen, may not happen. Okay, but approach delay is 99.9% of the time is there. So you are approaching. If the signal is green, you may slow down. Okay. Then we have time in queue delay. The car stop in the queue. Time is in the queue.
Yes.
Okay. Time when the car is in the queue. Is it equal to stop delay? No. Because the queue can. Yes. The queue can include moving time as well. Okay. You can be in the queue and can be moving. Obviously, this is how you clear the intersection, right? When you come, the signal is red. You have 3 cars in front of you. You join the queue. You stop. A signal becomes green. You won't come out of the queue. You move with the queue, right? Okay. So time in queue delay can be higher than stop delay. Time in queue delay may not have any stop delay. Okay. It was a queue, but before moving, start moving with it. And then we have the travel time delay, the one which I told you earlier, the general, okay, the actual travel time and the ideal travel time. Okay. And this generally applies to road segments, okay, but you can apply the same to intersection. So we have talked about 4 types of delays, okay, stop, approach, queue, and travel time. 3 of them you can see here, they are written there, okay, in this diagram. What is this diagram showing? It is showing actual and ideal trajectory of a vehicle. Actual and ideal movement of a vehicle. Okay. So you have time on the x-axis and distance on the y-axis. Okay. So at every point you know how much time the vehicle has consumed and how much distance it has crossed. Okay. Then it reaches here. Now this, if I'm talking about an intersection, okay, so this, at this point, at this time, or this is the distance where it has reached, or where it is doing what? Stopped. Okay, so this is the point of stoppage for the vehicle. Before stopping, you see what? A change in slope, right? So this change in slope is indicating what? Approach delay. Is this approach delay? What is happening here? When the slope changes, what is happening? What is happening with the speed? Here it is decreasing, right? Then it becomes flat, which you are saying is stopped. Then it changes again from flat to something else. What is happening to the speed here? Accelerating, it's increasing. Okay. This whole thing is approach. So it includes this one and this portion as well. Okay. Only this one, stop. Okay. Now if somebody plotted this line of the car without any stoppage, without any change in speed, okay, and he took the free flow speed. So he plotted a line. If the car started moving from time 0 at free flow speed and continued, okay, this will give me the ideal time. Okay, and if you take the difference between them, that will give you travel time. Right? There, you can see the approach delay, you can see the travel time delay, you can see the stop delay. This diagram shows you, or can show you, the time in queue delay as well. Time on the x-axis, now on the y-axis we have number of vehicles, total number of vehicles. Okay, so vehicle upon time is what? Vehicle upon time is what? Vehicle upon time is nothing. This thing. Vehicle upon time becomes distance. Nobody knew that. Volume, right? Volume or flow. Volume or flow. So when you see a line, like in the last figure, when you see the line, it shows you the speed, right? The line is changing, that means speed is changing. Here you see the line represents slope. Okay? So green time, there is a flow. Okay? Since the signal is green, this flow can be coming or going because there is no stopping, right? So they are same. Signal becomes red. This flow continues. Which flow can continue? Flow which is coming or flow which is going? At red, which flow will stop? Coming one or the going one? Going one will stop, right? So the arrival, they call it the arrival. The arrival continues and the departure stops. Clear? This will start moving again when the signal becomes green. Clear? Okay? Yes, there is red time, there is all red time and there is yellow time. Maybe what? You have green time. Okay, cars are coming, so there is a coming flow, and because the signal is green, they can leave as well. So there is coming flow and there is going flow, arrival and departure, both. Signal is red. Will the car stop coming? No. Okay, so they are still coming, but this one becomes flat. So which one is this? The one which was leaving. Okay, the leaving one became flat, and the leaving one will start again when signal becomes green again. Clear or not? Any questions? Okay. Now, if I pick any point here on this axis, remember this is number of vehicles, right? So this vehicle entered here, entered at this time, and it will leave at this time. From here to here, it was in what? During this time, this vehicle was in what? It was not only stopped. Here it is moving as well, right? But this is included. Now moving time is also included. So which time is this? This is, what type of delay is this? There is no speed here, so we cannot say. Yes? Approach. Stop. Q delay. Okay, time in Q delay. Okay, there is no sense of speed here, so we cannot say. Maybe it's approach. Okay, but approach delay may continue. Okay, this time the car has crossed the signal. Okay, approach delay will be when the car regains the speed. It has crossed the intersection, but it doesn't mean it's going at the same speed at which it came. Okay, so we are not sure. Maybe it reached the speed, maybe. We don't know. Okay, but from here to here it was in the queue. We know for sure, right? From here to this time it was in the queue. So this WI is a time in queue delay. Okay, and this is the thing about the other delays and this one. You cannot combine them in the same picture. Okay, so the other three delays were there, and this one which was there is in this picture. Okay, so we have the waiting time, which is the time in queue delay, and then you have this thing. Okay, so remember now, this is the flow, which is, this line is for going, right? Departure. So this is the people who are, these are the people who are going. These are the people who came. Okay. So what's the difference between them? We call it what? No, it's not time. It's number of vehicles, right? No. These are number of vehicles, not flow. Flow will be then upon time. Which vehicles? Vehicles which are where? In the queue. Okay? That's why they wrote queue. Got it? Okay? This is queue when the time is equal to this much. So you want to see how much is the queue at time t, you can come to this graph and have a look at it. What is the queue here? 0. Okay? Because there is no difference between these two. What is the queue here? 0. Okay? Then you see different values of queue, right? Okay? So at each time you may have the queue length changes. Okay? The queue length is changing. Okay? The flow rate at which the vehicles are coming, we are representing it with small b, the arrival flow rate. Okay? Arrival flow rate is small b. And then we have the flow rate at which vehicles leave. We call it the saturation flow rate. Small s, the correct term for it is saturation flow rate. But what it means is the rate at which vehicles will leave that is. There? Okay. There? Okay. There was a guy named Webster. Okay. He was there in 1958. Okay. Didn't have any industry. So it was looking at signals. Okay, and he gave this very simple equation for calculating the delay at a signal, the uniform delay. He called it the uniform delay. Okay, what is calling it the uniform delay? Any vehicle which comes on the signal is expected to be delayed by this much amount because of the signal. Okay, so this is the normal delay of the signal itself. Okay, when will it become non-uniform? Meaning when this equation will not work, when the queue becomes very long. So now the delay is not only because of the signal. That signal is still working, right? So if it was, sorry?
Doesn't change over time.
Change what per time? Uniform delay, yes. Okay, because we will consider the volume as well. So volume increases, the delay is supposed to increase. Okay, but in this equation, the delay is increasing or decreasing as a function of the volume and the time of the signal. Okay, but there are conditions. So the signal is, for example, 30 seconds green. Okay, so you came there, it was green for 30 seconds, then red for 30 seconds, and so on and so forth. So whatever delay happened, that was uniform delay, normal condition. Okay, if the volume is higher, the delay will slightly increase with this time. Okay, but in extreme cases, you come to the signal and there is a very long queue. Okay, signal is still working on the same time. Okay, but your delay will not remain the same as a normal time, as a normal rotation. Okay, because now the queue is not letting you go to the signal. Right? The signal becomes green, the queue is so long, you cannot reach the signal. So now you are getting until you reach the signal. So you are, the first 3-4 cars. So after 5 minutes of signal becoming green and red and green and red, now you are in the first 3-4 cars. So now you know that signal becomes green, it's my time to go. Okay, so then for you, it becomes uniform delay. But what about the people behind? Okay, not you. Their uniform delay will start when they reach near the signal. Okay, so then this equation will not work here. This equation does not consider that situation of very long. Got it? Okay, what do we have in this equation? Half red time into volume of vehicles. Okay, half red time into volume of vehicles which are in the queue. Clear? Simple? Very simple, right? This we don't like. So we will destroy it. Okay? So, we start the destruction with red time. We do not design red time for a signal. When we are designing a signal, we do not design red time. But signal is red most of the time, right? It's from Allah. We don't do this. We don't design red. Okay? We design what? We design green time. Okay? What did he say? We design green time. Okay? So what is red time? The remaining of the green time. What am I? We are designing time for movement of vehicle, right? Movement of vehicle happens during green time. Okay? So whatever is ungreen is basically red time. Yeah? Okay? Now this is a very special type of green. We will not go in details, but this green basically involves everything. The yellow time and all that. This is not the green light. Okay? That's why we can use this equation. Okay? So this equation, whatever it's saying is true. Okay? As that whatever is not green, 1 minus. Okay, what is my C? C is the cycle length. Okay, so if I do G upon C, it comes out to be, let's say, 60% or 0.6. Okay, so the remaining part, which is 0.4, is red. Got it? Okay, So when you do this and multiply by C, it will give you how many seconds of red. Got it? Clear? Okay. One thing done, we destroyed the R. Okay, destroyed means we expanded. Okay, then we have the flow. The flow in the cube, we need how many vehicles were in the cube. Okay, we can calculate the vehicles which arrived during that time. Let me check. Yeah, in the cube, yes. We can calculate vehicles which are in the cube in two ways. Okay, you see this graph over here? Okay, so the slope, which is V or S, okay, which is the flow, right? Vehicles per unit time. If I multiply the flow with time, I get number of vehicles. Okay, which vehicle I want? The vehicles which are in the cube. Okay, when did the cube start? And when did it finish? Okay, this is the red time. After red time, the cube will not finish immediately. Okay, it will take some extra time after red to move. Okay, so this extra time is called as TC, clearance time. Okay, so the signal became red. Vehicles were coming, they were getting in the queue on the signal. Signal became green. Now these vehicles have a chance to move. Okay, when will all of them move? After TC seconds after red. Where? Alright. Where? No. When the signal just became green, there was a queue, right? Which one?
After this time.
After this line?
Yeah.
Yes.
After the final target.
After this line, these vehicles which are in the queue, they start moving, right?
Then they start
Moving. In the green they will move, right? Up till green, up till red, they were not moving. So the queue was increasing, right? So now let's say when this happened, when signal became green again, there are 10 vehicles in the queue, right? These 10 vehicles need some time to pass, right? So TC is that time. Got it? Okay? So, understood? Clearance time, TC? Everybody? Okay. Going back, I want to calculate how many vehicles are in the queue. Okay. I will use flow into time. I use flow into time. I have two types of flows, this one and this one. I can calculate using this thing or this thing. Okay, both of them are weaker than the queue. So in the end, both of them are same. Okay, if I am using this one, flow into time, right? Flow into time. How much is the flow? V. How much is the time? Right? Plus TC. Got it? So if I use V, then it will be TC plus R. This will give me how many vehicles in the queue. Got it? So I use this line, the upper line, the arrival line. Okay. I can use this one as well, this flow as well. Okay. Is there a flow here? For this line, is there a flow here? No, right? So this one during red is 0. Okay. So there is no S into R. There is only what? S into what was this time? TC. Got it? Okay. So S into TC. This is what they are doing. This is when you use this flow. So this is happening during R as well as TC. And if you use this flow, then this only happens during TC. But in the end, both of them are weaker in the queue, right? So both of them are equal. Okay. From here, I want to find out the equation for TC. Okay, so I made both of them equal and found out what is the value for TC. Clear or not? Any questions? Okay. V equals in the Q. V. It is V into R plus TC, right? V into R plus TC. R remaining of green time. Okay. TC this thing. Okay. So I put all these back in the on this side. Okay. Clear or not? So when we do this, V becomes this. The number of vehicles in the queue after we put R and TC and everything. Okay. And you are calculating uniform delay, right? So that was half R into V. Okay. So R is the one which I showed you, and TC is this whole thing. So the final equation is this. Okay. This is how we destroyed the world. It was very simple, and then we made it into this. This is U before UOB, this is U in UOB. Right? Okay. A short form, right? This is called aggregate delay, meaning total. This will give you total delay for all vehicles. Total delay for all vehicles. So, for example, there were 1,000 vehicles. One of them delayed by 2 seconds, another one delayed by 10 seconds. Another one delayed by 50 seconds. If you add all of them, okay, you will get the first thing. Aggregated total. Clear? Okay? And if you divide it by the number of vehicles, if you take total and divide by number, it becomes what? Average. Okay? So if you take the first one and divide by the number of vehicles, it becomes average, and the last equation is for the average delay. The first equation is for total delay, the last one is for average. Clear or not? Any questions? Okay. In the last lecture, we have used this equation. Capacity equals saturation flow rate into G by C ratio. Okay. Saturation flow rate is the ideal flow rate, and G by C ratio is the available time. Okay, so ideal flow rate into available time gives you capacity. Okay, now in my equation, well, this is here. Huh? In this equation, I don't have, I have saturation flow rate, right? I have S. So I want to replace S here. Okay. So if capacity equals to this, then S equals to this. Okay. So I go back to this equation and replace S as well. Got it? Okay. So when you replace S, your final equation becomes this. Okay. In this final equation, I have V by C ratio. If you go to the equation for delay, you will see V by C ratio is represented by X. Got it? Clear? Any questions? Okay. So this is the final equation for uniform delay. Why are we using X here? Because X is our design parameter. So we are using V by C ratio here, right? And when you change V by C ratio, cycle length changes, right? So V by C ratio is the design parameter. So now we have the delay equation, which has a design parameter inside it. It's at 2 design values now. This equation has 2 design values or 3 design values. G, C, and X. Okay. So based upon your design, you can calculate the delay. Okay. So this is why the equation is modified. Okay. So very simple example. We have intersection approach, which has a flow rate of 1000 vehicles per hour. Saturation flow rate is given, cycle length is given, G by C ratio is given. Then give this G value, then give you the G by C ratio, okay, which is what we need in the equation. And they need average delay. need average delay. Okay. Anything missing? This is the equation which you see down. What is missing in this equation? The x is not given, right? We gave the g by c ratio, but x is not given. Okay. We choose. Should I choose?
From table. Maybe from table.
Maybe from this table. Yes. Should I choose? No. X was V by C, right? Flow rate, okay, upon capacity. Flow rate upon capacity. Which of them I have? Flow rate is given, right? Flow rate is given. 1000. Is this capacity? If this is capacity, then it becomes easy, right? Just take the not capacity. It's saturation fluid. Okay? This is saturation fluid. The difference between them is saturation fluid does not consider signal loss time. There is no loss time in saturation fluid. The actual capacity has the loss time, right? Signal becomes red, people stop, then they need time to move, they are in the queue and so on, right? Okay, so the difference between capacity and saturation fluid. So they are not equal. Saturation flow rate is not equal to capacity, but saturation flow rate can give me the capacity. Okay, they gave me saturation flow rate, right? And they gave me G by C ratio. Okay, so what is the capacity here? Saturation flow rate is 2800 and G by C ratio is 0.55. So my capacity is how much? One five four zero. Okay, meters per hour. Now I can calculate V by C. Okay, V is 1000 and this is 1540. Now how much is my x? 645. Okay, so now I have everything. What is the delay here? One four. This is the average, right? This is the average. So, seconds per week. Okay? If somebody asks me to calculate the total, what will I do? If the total delay is required, what will I do? We will use this equation, right? Or we can do what? Okay? Left? Any questions?
From that equation, what we
Sorry?
compare the C?
We didn't convert the C. It was not C. It was saturation flow rate. Why? You see the difference? 1540, 2800. They are not even close. Okay? Saturation flow rate means if you come to the intersection, there is no signal for 1 hour. Okay? Signal is green for 1 hour. Before you came, it was green, and for the next 1 hour, it will remain green. So that is saturation flow rate. So this cannot be the capacity, right? Actual capacity cannot be. Okay, anything else? What? Okay, so we'll start the presentation from Monday. Like you are how many? Can finish on Monday. Next week. Okay. Okay. can submit the report after that. No problem. 11 what? Then I said after. Next Monday is 11, right? Next Monday is 11. Okay. What day? 10. 10. Not final? Work progress. Finished. Done. 11 May final presentation. So final report. There is no progress. I didn't do any progress. What happened?